Hi, I am K. Narsimurthy, working as an assistant professor in the Government First Aid Women's College, Tumkur. I am going to discuss a very important theorems regarding the electrical network, and that is superposition theorem. Maybe in the second PUC level, you have studied some of the theorems regarding the electrical network, and the very basic theorems that you might have studied in the second PUC level is the Kirchhoff current law and the Kirchhoff voltage law, of course, the Ohm's law. These are all the three laws which you have been using from the second PUC to analyze the electrical network or to solve the problems regarding the electrical network. But when you come to a complex network, these complex networks cannot be solved so easily from the basic Kirchhoff current law and the Kirchhoff voltage law. This needs some other theorems. And the theorems which we require to analyze the complex networks are the Thevenin's theorem, superposition theorem, and the maximum power transfer theorem, and the Norton's theorem also. So I am going to discuss one of the very important theorem, and that is the superposition theorem. So I am going to directly to the statement of this theorem. In any linear bilateral network consists of two or more energy sources, the current or voltage in any part of the network is equal to the algebraic sum of the current or voltage produced independently by each source. This is the statement of this theorem. Now I am going to explain this statement with these three figures. So figure 1 shows the linear bilateral network. Linear in the sense all the three resistors which you are seeing in the figure 1 are fixed, constant. The resistance are constant. There is a proportionality in the circuit. So there is a linearity in the circuit. So it is called linear circuit. Bilateral, linear bilateral circuit. Bilateral in the sense the magnitude of current which does not depend on the polarity of the voltage source. Right. This is a linear bilateral network. Of course, this consists of two energy sources, two voltage sources of EMF E1 and E2. These are the two energy sources. Now, I am looking at the current at one part of the network, and that is across the resistor R3. So, the current across the resistor R3, which I am labeling as I, is equal to the current which are produced independently by source E1 and E2. Now I look at the current which is produced independently by V1. Look at the figure 2. In the figure 2, I have retained only one battery of EMF E1 and the other battery is removed and shorted. Now I1 is the current flowing through the same part of the network which is across I3 from the source E1. And look at the figure 3. I have retained only the second battery E2 and the first battery is removed and shorted. Now the current flowing through the same part of the network R3 is I2. So I1 and I2 are the currents flowing across the same part of the network which is produced independently by each source E1 and E2. Now I am taking the algebraic sum of these two. Algebraic sum means if the currents are flowing in the same direction, I can easily add these two currents. Since in these two figures currents are in the same direction, I can take the algebraic sum as I1 plus I2. Now this algebraic sum should be equal to the current which is flowing in the main figure 1. So according to the superposition theorem, the current I is equal to I1 plus I2. This is how we can explain the superposition theorem. Now I will go to the proof of this theorem. For the proof of this theorem, I am considering the same complex network which is shown here in the figure 1. Now here we have two batteries, the same circuit, two batteries, three resistors R1 and R2, R3, and it consists of two loops, loop 1 and the loop 2. Now here the current flowing through R1, I am labeling it as, I am calling it as I1, and the current flowing through R2, I am calling it as I2. According to the Kirchhoff current law, the current flowing through this R3 would be the I1 plus I2. Current entering the junction is equal to the current leaving the junction. So the current flowing through R3 would be I1 plus I2. Now by knowing all this, I can go to the derivation of this. First part I am analyzing using the KVL. So applying KVL to the loop 1. This is the loop 1. So what Kirchhoff voltage law says is it is the sum of the product of current and resistance is equal to EMF of the loop. Now I'll do one by one. Now I will look at the resistor R1. R1, it's a product of current and resistance which I have to take. One important note I want to make it here is your consideration, either you are going clockwise or anti-clockwise. If current goes in your direction, you have to take positive plus. If the current is going opposite to your consideration, you have to take minus. So yeah, I'll start with this circuit element R1. The current is I1 and the resistance is R1. I am going clockwise. Current is also going clockwise. So it is plus I1 R1. I have not mentioned plus here. Plus. Next I am coming into the R3 resistor. Here the current is I1 plus I2 and the resistance is R3. And the product is I1 plus I2 into R3. And the sign I have to mention is I am going clockwise, current is also going clockwise, it is plus, is equal to EMF of the battery. Here mentioning the EMF, we have to be very careful. If I am going from positive to negative, I have to mention plus E1. If I am going negative to positive, I have to mention minus E1. That's it. Okay, now I got this equation. Now here there are two variables I1 and I2. I will separate these two variables. I1 plus some coefficient into I2 is equal to E1. We got equation 1. Now exactly in the similar way I am applying the Kirchhoff voltage law for the loop 2. Here in the loop 2, one thing I am making a very different approach here is I am going anti-clockwise direction to avoid the negative sign. So since I am going anti-clockwise, current is also going in the anti-clockwise direction. So I have to take I2 R2 with the positive sign, because both are in the same direction, plus the current through R3 would be I1 plus I2 into R3, again the plus sign, current is also going anti-clockwise, is equal to the EMF of the battery. It is plus E2 obviously, because I am going from positive to negative in an anti-clockwise direction in the loop 2. Now exactly in the similar way I am separating the variables I1 one side and the I2 other side. I'll get this equation 2. So I have got the two equations. Now we have two variables which is I1 and I2. Two variables, two equations are very easy to solve. We have a method to solve this equation. I am applying a Cramer's rule for solving this equation. Yeah, I'll simply explain this Cramer's rule. If I want one variable I1, so you have to write the two matrix, one matrix in the numerator, another matrix in the denominator. Here in the numerator matrix, the first column would be the constants of these two equations. Obviously constants are E1 and E2. I have written the constants. In the second column here would be the coefficients of I2. Here the coefficients of I2 is R3 and here the coefficients of I2 is R2 plus R3. In the second column I am writing the coefficient of I2. In the denominator, first column would be the coefficient of I1 and second column will be the coefficient of I2. This is what the Cramer's rule is. If I want I1 in the numerator second column, I have to write the coefficient of I2. Right. Now I'll simplify this. E1 into R2 plus R3 minus E2 into R3, which comes in the numerator. And here in the denominator, R1 plus R3 into R2 plus R3 minus R3. After simplification, the denominator R3 will get cancels. If you look at the denominator, R1 R2 plus R1 R3 plus R3 R2, I can write it as sigma R1 R2. I can write the denominator as sigma R1 R2. Yeah. So I1 can be written as E1 R2 plus E1 R3 minus E2 R3 divided by sigma R1 R2. Now the next thing is to find out the second variable, which is I2. Second variable, you have to be careful while applying the Cramer's rule. There is a negative sign here. So it is minus of the first column, as we know it is a constant, and the second column in the numerator will be the coefficient of I1. But denominator will be the same as that of I1. So it is a coefficient of I1 and this is the coefficient of I2. Now it's easy to simplify the matrix. So E1 R3 minus E2 into R1 plus R3 multiplied by the negative sign, I'll get this. Now in the denominator also R1 plus R3 into R2 plus R3 minus R3 square. Here the R3 square will get cancelled. We'll get in the denominator same as sigma R1 R2, and if I add these two I1 and I2, I'll get I. So I1 and I2 added, I'll get I. This will be the equation 1. So I got the equation 1. I got the current which is flowing through R3 with both the batteries together, E1 and E2. Now I'll apply as superposition theorem says. Now I'm looking at the current which is produced independently by the source E1. So for that, to find out the current through R3, I want the main current which is drawn from the battery. So main current drawn from the battery can be found out by the simple Ohm's law, which is voltage divided by resistance. So voltage is the EMF supplied, which is E1, and the resistance is a little complex thing. We have 3 resistors here, so we need to think which is series and which is parallel. For the current I, R1 is in series and R2, R3 will look parallel. So it is R1 plus R2, R3 divided by R2 plus R3. So we will have a branch current formula. I1 is equal to main current into resistance in the another branch divided by sum of the two resistances. Another branch would be the R2 branch. Because I am finding the current through R3 branch, another branch will be the R2. Now the same I1 I am substituting. So I1 equals to, this is the main current which I have substituted, and this is the quantity which remains. So little simplification if I do by taking the LCM in the denominator, I can now cancel out this R2 plus R3 with this R2 plus R3. I am left with a simplified equation of E1 R2 divided by sigma R1 R2. Now I am going to find the current which is produced in the same part of the network, that is R3, by the another source E2 independently. Okay, right. For that also exactly the same thing I am applying. I am calculating the main current. Main current will be the simple Ohm's law, voltage by resistance. So we have a little careful. Here the R2 is in series, R1, R3 are in parallel. So it is R2 plus R1, R3 divided by R1 plus R3. After that, the branch current formula, main current into resistance in the another branch. But this is a little wrong thing I have written here. Resistance in the another branch. Yeah, there is some problem with this. Yeah, I'll go back to the same slide. Yeah. Resistance in another branch I have written as R2, but it is not R2, it is resistance in another branch is here it is R1, but by mistake I have written R2, so you please make it correct as R2. So for little further simplification, I am substituting I here. I'll get this equation, taking LCM, cancelling R1 plus R3, I'll get this equation. Now I'll get a simplified equation for I2. So this is the current produced independently by the source E2, and earlier I got an equation I1 which is produced independently by the source E1. If I take the algebraic sum of these two, I am getting an equation 2 which is exactly similar to the equation 1 which I have calculated by taking both the currents into consideration, both the EMFs into consideration. So equation 2 is the algebraic sum of the currents produced by each source independently, and the equation 1 which I got, the current and the same part of the network produced by both the sources together. So equation 1 and equation 2 easily proves the superposition theorem. So thank you for listening my lecture.